Just about there, folks. We'll make it official in about 5 seconds. Well, it looks like we can start. Welcome back, folks. We're now into week 2, and we're getting a feel of how this goes. This is pretty new to me. Usually when I'm teaching a class, even an online class, I'm in a classroom, and there's sometimes people in the class, people in the online Zoom section, but this is all weird to me, kind of new, where I'm just opening up a laptop in my basement and going at it. But let me know if you encounter anything that's weird about doing this class, whether it's looking at the recorded lectures, any problems looking at the old notes, and I'll try to get these things sorted out as those issues come up. Well, any questions at all, folks, to start us out today?
I haven't done the homework for this yet. Should maybe do that at some point.
Yeah, that sounds like a good idea.
Sorry, I think that was an open mic. Other questions or comments so far? Okay, well, I do have a set of announcements here. We are, let's see, going from bottom up, I guess. We're on example 3 of the section 2.2 notes. So we'll have those finished out pretty quickly once we start class today. We'll move into the very next section, 2.4. That means the due date is now considered official on this one. And there's always going to be a 1-week turnaround on the due dates for each one of these sections. So if there's a missing due date, that means we may take an additional day. I'm not completely certain we're going to finish those notes on that given day. Also, we had our first quiz that's posted. This one's going to be due Wednesday, and it's really just what we did at the very beginning, first couple problems on the section 2.2 here. There's not a whole lot of announcements, but any questions so far, folks? Okay, and then going through other announcements, I did add a couple more documents to the website. You might have noticed in section 2.2, we're starting to pick up a lot of different algebraic techniques. And the further and further we get in the course, the more algebra we're going to be reviewing. So if you scroll up to at the very top of the Moodle website, under the graphing calculator Desmos, you'll see that we have exponent laws review material and a worksheet to go along with it, logarithms review material and another worksheet to go along with it. And I'll be posting more of these kinds of things, probably within the weeks under a section as we get going. So if you feel like you're a little rusty on any of those ideas, exponent laws or logarithms, I don't think that's too unusual. I mean, if it's been a while since you looked at those ideas, it can get rusty. This is your one-stop shop to pick up those ideas and get some really quick practice in. And if you have any questions about any of this material, don't hesitate to directly ask. I can post additional resources as well. So that's where we're at so far, folks. We're in section 2.2, just about to finish it off. Any questions at all, folks, about how WebAssign is going or anything like that before we get into section 2.2? Okay, well, let's get started. We left off right here. Oh, no, that's the top of the notes. Let me try again. We left off, let me fix the participants window so I can see who was all in the class. We left off way down here, where we have a couple more formulas to take a look at for limits, one as you go to negative infinity, one as we're going towards positive infinity. We're really going to expand a little bit on this section. Sometimes on these notes, if you notice a lot of white space, it means we're going to add some information. Some of the things you might wonder about this are, why in the world are these two limits true? They just come out of nowhere. It's motivated by, first, these kinds of graphs. For example, if your limit is heading towards positive infinity, and there happens to be a horizontal asymptote, the limit will exist, give you a finite number, -2, and that's your horizontal asymptote right here. Likewise, if you're going the opposite direction, towards the left, negative infinity, then the only way you can put a finite number here is if there's another horizontal asymptote on the graph. So with those brand new limits on the bottom of the notes, that's essentially all that's going on. These are exponential functions. They happen to have horizontal asymptotes, and that's what allows these two limits exist. I feel like this picture is kind of incomplete. Let's add a little bit of information to this and explain even further why these are plausible limits and what other limits might be related to these. Any questions first, folks, before we take a look at a couple of those limits? Okay, well, really to start out, pretty much what these new formulas are all about is really, back here on the Moodle website, just reviewing information about exponential functions. So it's relative to this material right here. First thing I'd want to do to kind of explain these is just plot these functions. There's two of them, e to the x, e to the power of negative x, but also be careful what it's saying in the limit. We have a limit heading towards negative infinity and a limit heading towards positive infinity. So those have to be taken into account as well. So first, let's put it down a graph for the function in blue, y equals e to the x. If we were to plot this one, it would go about like this. So that's y equals e to the x. And this function does happen to have a horizontal asymptote. Anyone happen to know what the equation would be? Might be digging deep. This is kind of old review from pre-calculus information.
Wouldn't it be like, I mean, it'd be negative, right? If you're going negative across the x-axis.
Well, this curve is kind of interesting in that it never actually crosses the x-axis. So there will be a horizontal asymptote, but it wouldn't be negative on this one. And I kind of drew this a little bit funny. Let me see if I can draw it better. That would help out. This curve crosses right at 1 on the y-axis. If you're going off to the right, it looks like this. It's exploding, just blowing up. If you're going to the left, it looks more like this. Someone through chat says y equals 1. Close. It turns out it's going to be a little bit lower than that. Any other volunteers for what the horizontal should be? Good call, Medicine. I think this is a good group effort on this one. Again, this is just kind of old review material. Sometimes these are kind of shaky kinds of questions, but it's absolutely y equals 0. Good call. So that's the idea of the exponential function. If you're going to the right, it just goes up, up, up out of the page on this one. If you're going towards the left, the height of the curve gets closer and closer to the value of 0, but it never actually hits it. Since you're allowed to get as close as you can like to a value of 0, that means there is a horizontal asymptote. Let me kind of draw it like this, of equation y equals 0. So that takes us here. If you're writing out to this limit, let's just rewrite it again so we can visualize it better. The limit as x goes to, we're thinking about going to the left, so we have to put in the negative infinity there of the blue function, e to the x. This limit must be 0. And I think the color coding will help. Let's put in 0 in purple. I guess that's probably indigo, but let's see here. No, that is purple. It's going to be 0 here, only because of that horizontal asymptote. So that's the explanation of this limit. But there's really two interesting limits for this function. There's the one where you go to the left, so watch for the sign here. But if that sign became limit, x goes to just infinity, e to the x. Anyone see what this one should come out as? It turns out it wouldn't be 0 on this one, but the thing that we should check first is what's happening on x. If it's saying x tends towards infinity, then we're going on this portion of the curve. So we're essentially somewhere out here. And as Jana said, yes, this one's going to turn out to infinity. That's only because if it's going up without bound, never stopping, then down here we say equals infinity. So those are two interesting limits relative to y equals e to the x. Just to finish off the notes, for the sake of completeness, we'll do the e negative x one. But any questions first, folks, with either of those two limits? Okay, and actually kind of like this circled here. Let me circle this equals infinity. And this portion, just to convey that's the reason we went to infinity there, it's just shooting up. One question was, why is the horizontal line the positive infinity? let me see here. Are you referring to this purple one right here where it says y equals 0 for the horizontal line? Or are you referring to just the infinity right here on this limit? Oh, gotcha. Well, this was just an additional example just to see what happens to a positive infinity on this one. So it was just like an extra example that we were looking at. Am I getting understanding your question on that one? I feel like I might be missing something. Oh, gotcha. Thanks for asking about that. So a vertical asymptote has to have a function that has more of this kind of behavior. Let me put down just a little bit of extra white space down here. Actually, vertical asymptotes are really very special when it comes to this kind of idea. And let's say we have a vertical asymptote at maybe it's 1, 2, 3. Then the function can do some really interesting things. Let's draw a function that looks kind of similar to it. The last one we were drawing. This is a function that goes up like this, attracting to the vertical asymptote. Then what happens right here at 3 is the function can never actually cross this vertical asymptote. So it could be really anything at all. Perhaps maybe the function goes like this again. And maybe it could turn down going in this direction, going left in that direction. So if you have a vertical asymptote going this way, you would say limit as now x approaches. Now this is section 2.3 material, but this is a really good question as a preview. Limit as x goes to 3 of the function f of x. This whole function here in both of its pieces is y equals f of x. This one would go off to infinity due to the vertical asymptote right here. But comparing it with the other problem, this one's a little bit different. It has no vertical asymptote. As you move to the right, the function keeps on going. It never has a point where it stops like this one. Nonetheless, the function keeps on getting higher and higher and higher as x moves further and further to the right. And that's what's producing the infinity on this one. Does that kind of clarify what was going on with those two related ideas on that, Dana? Let me see if I can zoom out on both of these. Okay, and sorry, Douglas, you had a question about this one as well?
So are you just picking arbitrary points on that graph to represent where you're going? Because like e of x is, I mean, those are variables, right? So you're just picking wherever it is you want to go.
Absolutely. So the direction you're going is always the x and the arrow there. So I wanted to do this one first just to illustrate the formula, why it's true. And then I just picked going the opposite direction towards positive infinity to show what would happen if you switched what was right there. Does that answer your question about that?
Yeah, but you can choose like to start up at like 3 on the y-axis, or you can choose for it to be anywhere on that graph.
Yes, absolutely. In the current notes 2.2, we really have two things we're doing, negative infinity or positive infinity. In section 2.3, we're going to take limits where it approaches finite numbers like that, which could be any number whatsoever. Other questions or comments, folks? Okay, these are really excellent questions, by the way. I appreciate them, especially for technical issues like these. Why this one has a vertical asymptote and we produce infinity, and this one still getting an infinity with no vertical asymptote whatsoever. In fact, just to piggyback off that idea, let's take down a really easy, nicer function. So here's a third example. If we have a function, say y equals, let's make it just x, kind of the nicest function ever. Whatever you pick for x, you've got for a y. If you plot that function, it's kind of a nice one to plot. It's linear. It takes a value of 0. When x is 1, it takes a value of 1. And so here's the entire graph. We just needed 2 good points. But this graph has no horizontal asymptote, has no vertical asymptote. So now we can fill in 2 interesting limits. Let's suppose you took the limit as x goes to infinity of the y function. I'll just put in x for it. And let's do another one, limit as x tends towards infinity. Oh, and I screwed up on that one. Let me try again. I want to change the direction. So let's say x goes to negative infinity of x. And I don't want to highlight everything on the document, but let's highlight this right here, because that's part of that struggle with these kinds of limits is double checking your directionalities that you see here and here. Okay, let's leave this one up to the class. Any volunteers for one limit or the other? Absolutely. Thanks, Eli. The first limit is positive infinity because, well, it says you're going towards the right. As x gets larger and larger, you're moving along this x-axis. But that means on this curve, you're just getting higher and higher and higher. This one heads off to positive infinity with this as a result. Absolutely, Dana. And this one, when we change the direction, we're saying x is getting larger and larger negative. In other words, just going to the left. But if you're going to the left, the curve itself is the guideline, and your y-coordinate is just getting smaller and, well, let me say it this way, larger and larger negative. It's just plummeting. So we put down negative infinity, as you said, on this one. So these are really interesting limits. There's a lot to say about this kind of stuff. And that's why I appreciate the questions. If we take extra time in chapter 2, because all of this is so strange, it's absolutely well worth it. So definitely always come armed with questions. I'm very happy to go through each and every one of them. But I think the biggest thing that's kind of confusing already is this one can produce a limit of infinity without a vertical asymptote. If there is a vertical asymptote, you can also get an infinite limit as well. And you might have no asymptotes as well, and still you have a limit of infinity and negative infinity on a curve. This would be one of those kinds of examples. But we did half of these kind of limits. I want to take a look at this one, and now this one next. Any questions or comments so far? Okay, here's our new graph. It's essentially the same as the e to the x graph, but there's one tiny, tiny little change. Instead of x, we put in a negative x, and that does cause a reflection. That negative right there, where the x value or the x variable is, causes the whole curve to flip across the y-axis. So imagine this page right here flipping around. The result would be you still connect through here right at 1. If you flip the point right here, 0, 1, you still get this point right here. But now this end, where it's going off to infinity, it looks more like this now. And as you go to the right, it hits another horizontal asymptote, really the same one at height y equals 0, but it's doing it in the other side of the graph. That means if we look at 2 limits, we'll see both of these here. We should get 2 different results. Let's go in order. We did negative infinity on this one, so let's do limit as x goes to negative infinity. This time the function is e to the power of negative x. So we're looking at this curve. Well, if we're heading towards negative infinity, based off the other examples we did, that means x is going to the left, so that way. And on the curve, you're heading up in this direction, just blowing up towards positive infinity. So here, we would get infinity, but notice whether you got an infinity or not, when x goes to negative infinity, totally depends on the function. If it's e to negative x, this one's infinity. If it's ordinary e to the x, you would have gotten a 0 instead. So lots of tiny, tiny little minutiae to pay attention to these things. But really, if you have a picture of the graph in the back of your mind's eye, then that's the major thing that you want to try to think about in order to resolve either one of those two limits. Likewise, on this graph, we did this one before on the left, so the related one will be limit x tends towards positive infinity of the function e to the x. Now, if we're heading towards positive infinity on this one, that means we're going along this directionality, and we hit that horizontal asymptote to y equals 0 once again, giving 0 in the limit. So that's a lot of stuff altogether. These are the two limits the book provided, but there's really 4 to think about through these two graphs. Douglas says, so the negative x basically switched the result. Yeah, that's a great way to think about it. If you switched from e to the x to e negative x, then you're essentially just trading off these two limits. So that's a really great way to organize that. Other questions or comments so far? Okay, well, with all that knowledge in mind, we have a couple more examples we want to get through. Well, first, I think I heard a question. Alif says, doesn't the bottom e to the x need to be negative? Oh, you might be right. Yep, I think I just miscopied that one. Thanks so much, Alif, for spotting that. One of these things definitely we wouldn't want to leave on the notes. I mean, if it's left on the YouTube video, mistakes will happen, but if we can correct the record, at least on the notes, that's a great idea. So this was e negative x here. I should have copied that function to match the one above. You bet. Thanks again for spotting that one. Other questions or comments so far? Okay, well, let's get down to the last couple of examples. On the last one down here, example 3, it simply says, well, find the limit. Kind of just the same instructions we saw in example 4. The function is odd. We are dealing with some kind of rational function, constant in the numerator, and 8 minus an exponential down in the denominator. So really, as you do a problem like this one, it's all about the limit laws. Let's review this one as we go, just to get a feel for that long list of formulas we had up here. So somewhere we have some limit laws. There they are. Again, this always feels really imposing, but here's how these are used really in essence. We take a quick screenshot. And we'll show once again how they're being used, but what you would typically actually write if you were solving a problem like this one, say on a quiz or an exam or in the homework. So you make this a little smaller and bring it up. Okay, so here's our new example. And if we were going to attack this limit, the first thought I would have is, let me highlight the law we're about to use. I want to visualize this happening. Really, we're going to be taking the limit of the numerator and denominator independent of one each other. So when that happens, you'd be taking the limit of the numerator, which is a constant 17. That's when limit law 4 comes in. That means this 17 right here is going to be unaffected. And now we move into, well, what's going to happen in the denominator? In the denominator, we have two functions, but we can split our limit amongst the two using limit law number 2 right there. That means you'd be taking the limit of 8. Well, that's a constant, so it stays in 8. And you have to take the limit of this one. So that's where all the fighting goes in. So with these 3 highlighted limits, this whole thing could be rewritten as 17 divided by 8 minus the limit as x. This one says negative infinity, so let's go and carefully put that in. X goes to negative infinity of e to the 5x. So now, if we can resolve this limit right here, our job is done. And really, we're only using 3 different limit laws so far to get through it. Any volunteers for what should happen on that one? if you're like me, it seems like there's an answer, but something feels a little bit off. I think ran into this kind of technical issue from before, but here's the first thought I would have. If it's e to the 5x, what's most similar to that? It would be this graph right here. And we know if we're heading towards negative infinity, we should be expecting a limit of 0 altogether, but that is not our graph, right? That's y equals e to the x, and our function is e to the 5x. So some way, somehow, we need to resolve this right here. In doing that, there's a lot of different things you could do, but here's maybe a clean way to visualize this. Let's do a little bit of scratch work on the margin to the right and look at the function y equals e to the 5x. What's interesting about that function there is if you use some exponent laws, there's further things you can do to it. You could say y is also equal to e to the power of x multiplied by 5. And the reason that works is in this kind of configuration, the exponent of 5 and the exponent of x must multiply together, resulting in that 5x. So if you have a function that looks like this, there's probably a limit law there that's going to help us out. And that would be limit law number 7. Let's take a look at that there. If you have a function f of x to a power p, our function is e to the x and 5 is the power, then the limit on the outside right there, much like we're dealing with this, can be commuted inside. So let's see how all that goes by taking just a couple additional steps. So next, this is equal to 17. 8 minus the limit as x goes to infinity. Let's break this up. E to the 5x is just as good as e to the x to the 5th power. And now this segment right here can allow the limit to go inside the parentheses or brackets raised to the 5th power. Jamie says, this is sort of off topic. Do we need to memorize all of these for the exams? I would say not every one of these things. Once we get closer to the exam date, there are some things that we are going to put on the exams. It's not going to be this table, but let me show you the one that is going to go on there. Oh, and thank you, Douglas. That should have been a negative infinity. That was my bad. That's one of the weird ways you could lose points on things is just a copy error. Always kind of heartbreaking. So thanks for correcting the record on that. I appreciate it. But let's take a look at that question Jamie was asking. This is a lot of stuff to memorize on an exam. But on a real exam, I would be handing out this set of notes. These limit laws right here are going to be on the last page of the exam. So those would be something that's actually included. And I agree, there's not the need to memorize every single little thing. But I think what you'll find is once you're actually studying for the exam, you're not relying on this as much. This is more of a list of things that you're allowed to take for granted. And we get used to just breaking out the limit without citing these every single time. But since we're learning it, I thought we should pull this up and see how these ideas connect. But other questions or comments so far, folks? Okay, let's keep on going. On the next step, this becomes 17 divided by 8 minus. Now the limit that's on the left here is going to go inside our parentheses. So this turns into limit x goes to negative infinity of e to the x. And the power of 5 would go outside right here. At this stage, we know that limit is 0 from the notes right above and the graphs we were taking a look at. And we can just say that this is 17. 8 minus 0, or 17/8 altogether. So this is kind of an interesting problem in a certain sense because there is always a huge shortcut to this sort of process. We didn't have a formula to e to the power of positive 5x, but we know if we do enough algebraic trickery, it shouldn't be any different from, let me scroll up for just a moment, this one right here. So if you can do some algebra to show that e to the x does come into the problem, then these are the steps to prove you really have the right result. But here's an additional comment I definitely want to leave here. You don't always want to do this every single time you do a problem. It might feel like you're reinventing the wheel. If you notice that this is going to have the same limit, then going here to here is an encouraged. And encouraged. One moment, my computer's kind of lagging as I try to write that out. Okay, let me try one more time. This, we have to try two more times. Something weird about the pencil tool. It starts to cause my document to lag. One moment, folks, while we finish this technical difficulty off. There we go. Okay, here's the comment I was trying to put in. This is an encouraged shortcut. So we don't always use the limit laws verbatim through the list. If we notice that this function is related to the formula above, we can go just right directly to here. We know that limit has to be 0. E to the x and e to the 5x are essentially the same type of function with just some small changes there. Well, any questions, folks, with the conclusion on the limit or the shortcut? Okay, well, we're nearly done with the notes. It's day 3 of the course, and we are still on the first section, but I think that's kind of normal. This is a pretty technical set of notes. The last thing we're going to do is just take the ideas we see here and see how it would go in an actual application. There is an application problem in your homework as well. Your function is not entirely similar to this one. It's slightly different, but the steps you're about to take are more similar to one of the limits that we did above. And Douglas says, are the notes from the class present in Moodle or just the blanks? I intend to have both on there. So when you go to the Moodle website and say, click on this one, 2.2, you should see everything that we were doing up to the day we finished on last Wednesday. Let me double check that. Yeah, it looks like we finished right here last Wednesday. So that means after we finish our work for today, I'll upload the 2.3 notes, the 2.2 notes, but there'll always be the blanks here in case you just want a blank sheet as well. Other questions at the moment? Okay, well, this will be our first application for the whole course. We won't have a whole lot of applications in chapter 2 when we're just developing the machinery we need for calculus. But as we get into chapter 3, 4, we'll do more and more applications throughout the course to see how all these ideas somehow connect to meaningful things in the sciences. And here's something meaningful in the sciences. This problem is about a Pacific halibut fishery. Halibut is excellent fish, so this is already an important problem for me. The Pacific halibut fishery has been modeled by this equation. So that's an odd equation. They tell us here, B of T is the biomass in kilograms at time T. They didn't tell us what T was, but we might think it's months or something in this problem. So they're asking, what is the limit as T goes to infinity, as time gets larger and larger, and what is the significance of that limit? So lots going on in this problem. First, when you look at this, I think this is probably the bigger keyword. It's good to kind of imagine that you are the business owner, maybe. Maybe you have some plot out there somewhere in Idaho and you're doing Pacific halibut fishery farming. When we say that your biomass of the halibut fish is modeled by this function, we just mean we looked at some data points and we felt that that one function seems to match the data points the best. So it's not going to predict how much fish you have, but it's going to be the closest way we can kind of look into the future, try to extrapolate what should happen to the fishery. So if you are yourself own a Pacific halibut fishery, you're very interested in these kinds of models because it's going to tell you whether or not you're going to be profitable in one quarter or going bankrupt in the next. So it asks us first, what is that limit? Let's first do the limit and then we'll try to explain its significance. So starting right there, we need to take the limit as time goes to infinity. So now we're just saying in the long run, let's put that there. If you ever see this in an applied problem and t is running, meaning time, we're just wondering what's going to happen to the model in the long run. So we're taking the limit as t goes to infinity of this thing, b of t. I didn't really get too far on that. All I did is copy down what we're about to do. Next thing we want to do is fill in what the b function is. So this is limit as t goes off to infinity of this whole thing, 8 times 10 to the power of 7. So that's a huge number, but remember this is biomass. So this is representing all of the mass of the halibut in kilograms. Below it's 1 plus 3 e to the power of negative 0.7 t. So this function is very similar to the one we had on the prior example, and we'll take the shortcut on solving what should happen on this one here. First thing to notice is we're constant in the numerator. We have a constant here, a constant multiplying. So that means finishing out this limit is all about what would happen to that function there. If we did a really fast plot of it, it would look like this. Even with a negative 0.7, it's still going to match the same shape of coming around like this, crossing at 1, and going like that. So this is y equals e to the negative 0.7 t. So anyone see what should happen to this quantity right here by the red dot as time gets larger and larger? Would that head to 0 or would that head to positive infinity? I agree with Eli. This one would head right to 0. So only because the limit here is as t gets large, it's moving to the right now, we take on the limit for the horizontal asymptote of 0, and that whole thing then becomes a 0 itself. So let's take a look at the next step. Here's where I would put in that shortcut. This turns into 8 times 10 to the power 7 divide by 1 plus 3 times 0. So in total, it's 8 times 10 to the power of 7. This was biomass, or where we started, in kilograms. So we can say that many kilograms. So we did it, folks. That's the first part of the problem. We evaluated the limit and got that quantity. Next thing we need to do is say what the significance is for this limit. In other words, what does that number mean? Imagine maybe you're giving a report to the owner, the business manager of this Pacific halibut fishery. What would you say after you tell them 8 times 10 to the power of 7 kilograms? Any volunteers for what the report should include or say? I'd say this is kind of tricky as well, by the way, since we haven't done any problem quite like this. So if you're not sure how to get started on this one, you could always begin about like this. Start where the limiter operator was. Douglas says, as time goes on, you have less fish. I wouldn't say necessarily that because, for example, when time was, say, 1 right here, you'd be dividing by 4. But as time got larger and larger, we ended up dividing just by 1. So that means the quantity actually increased to a certain value. But you're on the right track. I like how you started with as time goes on. We could say, oh, my document froze there for a moment. There we go. As time goes on, something happens to b of t. So let's switch gears and start talking about this. The biomass of the halibut grows to a level of 8 times 10 to the power of 7 kilograms. So in the long run, this is how much biomass you would expect to have as the owner of that fishery. And this is assuming that we've done nothing to it. We're just watching the population grow in its environment. So it hasn't been harvested, nothing like that's about to happen. So that's good information for the business owner because it's telling them how much are you going to be able to actually sell on this fishery if you didn't do any kind of harvesting whatsoever. This is the maximum amount of biomass that you'd be expecting if the model up here is accurate. Anything can happen. Maybe a disease enters into the fishery, and this number could be very, very off in practice. But if this is the best tools you have, trying to model what's going on in the fishery, people still give a lot of credit to these kinds of things. Well, any questions, folks, on how this application here worked? In the long run, is the biomass approaching 0 or 8 to the power of 7? It's approaching that 8 to the power 7. But that's a really good clarifying question because it's this portion right here. Let me get a new color. That had this feature and went off to the 0 value. So one portion of the biomass went to 0, but the rest of the total function increased to a level of that quantity there. Does that make sense in thinking of it in those terms? Okay. Other questions at the moment, folks? Well, we did it. That was our first section of the entire course. A few more to go get through, of course. But again, what happens with these notes is I'll be converting it to a PDF after class. Then I go over here and I just overwrite the notes here. So you're always going to have a record of what we did in class. It'll be a YouTube video, but going through an entire YouTube video just to look up something is kind of a terrible experience. So if all you need to do is find some quick problems, they'll always be uploaded right here as well. So we're going off next to section 2.3. Let me get that there. And now we're taking the limits of functions at finite numbers. Oh, sorry, I missed your statement there, Dana. Dana was saying the amount of fish levels out around that 8 to 10 power 7, that is the limit. Yeah, exactly. That's what's going on in this problem. This whole function right here would have had a horizontal asymptote right at that level, this value here. So in other words, as time goes on, the biomass in the fishery increases up to that level. Well, any other questions or comments, folks? You bet. Sorry for jumping to a new page right there without taking that question. Well, this one, you could simplify it 8 times 10 to the power 7, but for numbers that are that large, I'd say it's just fine to leave it in scientific notation. At this stage, I would say that's more of a stylistic choice, but I would say it's a good call to leave it in that format. Okay. Any other questions or comments, folks, on this one? Okay. And while we're looking at this, in the actual WebAssign homework, just to give a hint, the last problem in section 2.2 is like this one, but I think the function is more similar to something like this one here, for example. So you'd be taking the limits using this idea, and you get the same kind of results. Oh, I thought I had a chat. It seemed to have gone away. Sorry, I'm still figuring out the Zoom. Looks like Zoom got a little bit interesting and can reply to an individual comment. I didn't know I could do that. I might have just clicked on something weird in there as well. Okay, well, there's another really great question on these notes. That question was relative to how this one came out to infinity without there being a vertical asymptote. And that led us into a side example, a side discussion about that limit. And in all of the notes, there is only one limit that looks like that one. We call that a limit at a finite number, and that's what section 2.3 is all about. Here we take the limit as x tends towards some value a, where a can be any number whatsoever. So essentially the way these notes are organized, the textbook, is if you're in this section, then the types of limits you're taking are these, either towards positive infinity or negative infinity. So in other words, section 2.2 is about long-term behavior of the function. What happens if time goes towards the right or as x goes far towards the left? And then section 2.3 is now about what happens in the middle, the local behavior of functions. Let's put that down here just as a quick statement. This is local behavior. So we still have the same kind of ideas, but we'll go pretty slowly and carefully in section 2.3 because this section can be tricky in and of itself as well. But the good news is we have some intuition of what limits mean, and we're really just building off of that on these notes. These notes we may finish when we come back on Wednesday, but again, chapter 2 is a good chapter to go slow. So if there's additional questions, we'll take our extra time on these notes as well. So here's how the definition starts and a quick example down below. It begins by saying, suppose f of x is defined when x is near the number a. That already is a heck of a statement right there mathematically. It means your function is defined on an interval that contains the value of a, except a itself. So being defined nearby a allows us to potentially be undefined right at a. It'll just depend on the function. Then this statement right here means that as x gets closer and closer to that number a, maybe it's 3 or 5, the height of the function f is going to level out to becoming closer and closer to the limit L right here. So in essence, what this means is f of x, its values, get as close to L as you like by just making x sufficiently close to a, but x doesn't actually have to equal a. So that part right there in yellow and in bold, that's what makes this the trickiest. So we'll try to make sure we look at those ideas quite heavily, especially on this first example right here as we take a look. First, any questions, folks, on the definition here? Okay, so it's tough reading just the definition on its own without an example. So here's what our example looks like. And by the way, in section 2.3, much of the problems are going to look about like this. We're looking at problems from the point of view of just the graph. And then in section 2.4, we'll see how to do it using algebraic methods. So expect a lot of graphs in this, and it'll be the same in the homework as well. On this graph right here, we want to calculate f of 1 and the limit as x tends towards 1 of f of x. Let me just try to scroll down so where we can see the definition. Let's begin with this one. F of 1. F of 1 is not too bad, but it can be tricky on a weird graph like this one. This one has a type of discontinuity. The discontinuity is because if you were to try to graph this using a pencil, you would have to, at some point, pick up your pencil, put this dot in, pick it up again, and move it out. So if you have to draw a curve where it's necessary for you to pick up your pencil and go to a different spot, that would be a discontinuity. So there's a discontinuity right here. But nonetheless, we can still evaluate what f of 1 is, and potentially even the limit as well. Anyone see what the value is of f of 1 just from reading the graph? Yep, it's exactly 1. It's much like reading a limit. If it's f of 1, the 1 there is a value for x. So we go to the x-axis where 1 is. We move up until we hit the curve, but we have to stop right there on the solid dot that we see. The open dot is not a point on the graph. That's what this is trying to communicate with the open dot. So once we hit the graph, we move over. Once we take the value of 1, that means f of 1 is equal to 1. So halfway down, or halfway done with this one. We've got f of 1. Now we just need to produce the limit. This is where it gets really pretty tricky. So let's take, maybe a different color will help out. The limit as x tends towards 1 of f of x. We're going to take a look at this definition and do this one extremely carefully. So if this limit that we're writing down has a value, then it would be found by taking x close to a. In our problem, a is 1, on either side of a, but not equal to a. So this is the trickiest part of taking a limit at a finite number. The number itself, it'd be 1 right here, is totally irrelevant to the question. Just because f of 1 equals 1 doesn't say anything whatsoever about the limit. It turns out this one would be a limit of 2. So good call on that one. It wouldn't be a 0 on this one, but you're definitely on the right track. So if we're taking this limit as x tends towards 1, here's one really helpful strategy. Let me get that pen going. Because of this right here in bold by the red dot, it's telling us we actually don't care what happens right at 1. So you might find this to be a decent strategy. Just put a blinder right here because none of that information actually mattered. Next, it says we have to take x. Let me get a new color here. To be sufficiently close to a. A is our 1, and we just see what the function settles down as. So if you're taking the limit as x tends towards 1, maybe you might imagine you're right here at 1.5. You would have to go up, hit the curve, go left, until you hit the y-axis. My going left kind of got messed up. There we go. So at this value, we settle down to a height of, looks like 2.75 maybe. But we have to make x get closer to a equals 1. So you could get a little bit closer. Here, the limit gets closer and closer to 2. We need to zoom in a little bit. Now let's imagine we got to even closer. Let me get rid of those two. If we took a value that's right about here, right where 1 is, we'll hit the curve right about here and get closer and closer in that way. It's kind of hard because of that black line. Let's just take it off for the moment. We're about here. We'll go up, hit the graph. That's about where I should have hit. And yeah, it really looks graphically as if my numbers go to 1.1 or 1.05. I'm getting closer and closer to the height 2 because the curve is going down as we move towards the left, towards that 1. So that's what's happening as x is toward the right, but this has to happen on both sides at once. So you have to also be able to visualize if you come in from the left, say at 0.5, what's happening to those numbers? Here, the output is about a 2.5. If we get closer and closer to 1, because we want the limit as x tends towards 1, then here's a really close value. Right about there, I will get an output of about maybe 2.2. And visually, would you agree that as we get even closer to 1, it's hard to draw, these arrows going to the left would get closer and closer to 2 itself. Does that make sense to folks at the moment? Okay, so if we're happy with that, then as the limit as x tends towards 1 of the function f of x, it becomes 2 itself. And that's kind of a shocker in a certain sense. We had a discontinuity, sure. Let me just put a different arrow there to point so it's not in the way. But what's surprising about all this is watch out for what's happening to the function value. A function value like this one does not have to agree with the limiting value that we see over here. It all just depends on what's going on with the curve. I think these limits are kind of tricky, a little bit more tricky than section 2.2. So I have a lot more examples like this. This one was just meant to be a fast example to go along with the definition. So just to recap what happened on this one, if you're taking the limit and right here, it's neither an infinity nor a negative infinity, it's a finite number like say a 1 or a 2, then what we're doing is we're saying the limit is 2 if you come in from the right, the height of the curve gets closer and closer to 2 going down or up. And if you come in from the left, the height of the curve is also getting closer and closer to 2. Then that would make this limit correct. But notice again, that's a pretty big disagreement between those two limiting values right there. Definitely something we should practice more. Any questions, folks, so far on this one? Oh, that's a great question. Thanks for asking that, Cameron. Let's make the picture look like what it would be if there really was a does not exist. And I like that abbreviation, by the way. That's a good one for the notes. A common abbreviation that I use as well, that Cameron used, is DNE, means does not exist. And that is a really important acronym because plenty of things in mathematics does not exist, and we have to indicate that here and there. So what would make this one not exist would be if the graph looked like this. Let me see if I can change that. Oh, I have light gray, but I want white. Can I get a white on this? Maybe not. I don't think I have a white highlighter. That's kind of unfortunate. But let me just convey it this way. I do have a white pen. That'd do the job. Let's suppose that was gone, using my white pen to just eliminate it. If your graph looks like this, then over here, f of 1 would be undefined or does not exist. Yes, that's exactly right, Dexton. It was that solid point that gave us the function value. And Dan asked, why do we care for the f of 1 equals 1, since the function has a limit that inhibits it from crossing there? Well, there's nothing inhibiting the function from crossing through here. You could have a limit of 2. Well, let me get back to where the original curve was. So Dana asks, why do we care for the f of 1 equals 1, since the function has a limit that inhibits it from crossing there? And how are the two related practically? Okay, those are really good questions, Dana. Thank you for those. So in this particular problem, there's nothing that's stopping the curve from going through where x is 1. The only thing that potentially would stop us would be if we had a vertical asymptote, like on, this is just an illustration that we put down. A true vertical asymptote like this, your curve could never actually cross because it's attracted to the vertical asymptote. It'd have to come back, failing the vertical line test. So you could have a limit, infinity, over here, but the moment you have an infinity right there, there must be a vertical asymptote. Those are one of the things we'll see in our current notes. But the difference this time is this one came out to a finite number right at 2. So there was no vertical asymptote on this one. And that means there was no vertical barrier where the function couldn't cross it against. And really the major purpose of looking at this one versus this one was meant to show the function value can be different from the actual limit. So we're just fighting with the two to see how they compare. Jamie asks, maybe I'm jumping ahead, but don't we take the limit of 1 point greater than and 1 point less than 1? I'm not too sure about that question. Let me see here. Yeah, oh, I got your question. Yeah, when we take this limit, when x tends towards 1, also right here, highlighted in yellow, these are considered double-sided limits, meaning you have to have values when you're coming into the right of the function, and they have to be getting closer and closer to 2. You have to have values when you're coming into the left side of the function, also getting closer and closer to 2. And yes, that concept is on these notes right down below when we're going to be looking at these kinds of things. These are called single-side limits because, let's make that one bigger. There's a direction you're approaching. This says approaching A from the left. This one says approaching A from the right. So these limits have a certain directionality. But on these ones here, we have to be approaching from both sides all at once. Does that answer your question so far, Jamie and Dana? Awesome. Glad to hear that. Any other questions? There's this pretty weird math, first time you've seen it, so no worries if there's a lot. Okay, so big takeaway from these are watch out for the function values versus the limiting values. They do not have to agree. In fact, if they did agree, we would have said the function is continuous. In other words, there wouldn't have been a hole in the graph right there with a point defined right down below. But these are very tricky, so I felt like after looking at example 1, we should look at more stuff just like it. So example 2 is doing more of the same kinds of limits. This time we have 3 functions at once. Let's see if I can make that just a little bigger. We have a function f of x graphed above, g of x graphed above, and h of x graphed above. Now, if you're looking at that function and thinking, I could simplify it, good on you. That's kind of the trick of what's going on here. The simplification of this function results in that one. But you might have also noticed these are plotted really kind of strange. Let's actually put this into Desmos because this can be a real experience you might have as a student where you plot a function, your graphing calculator tells you something about that function, which is not factually correct all the time. So here's how that could happen. Let me open up a new calculator for us. I need to remember to open this before class starts, but here we go. So I want to put in this function, the f of x one we see here. So f of x equals x squared minus 1 division by x minus 1. So that's what the function looks like. Let's compare graphs. Here is the graph that I brought in as a screenshot, and it doesn't look the same as this graph right here. Let me bring in the viewing window. We're going -1 to 1, so let's get at least close. Yeah, these functions don't look totally compatible, but you just have to really explore around on this graph. This graph says that there's a problem right as x equals 1. And if we click along on this, what happens at 1? If I get right on there, this is kind of tricky. Bear with me. Oh, almost got there. There it is. Let me move this over. Drink way too much coffee for this. Okay, here we go. So right at 1, it really is the same kind of graph, and it's just undefined. It's a shame that the Desmos doesn't show that by default, but the way a TI-84 or Desmos is graphing these things is it's literally calculating points and connecting the dots. However, there is actually no connection right here. So on this function, we have a true discontinuity, and we can also say at the same time, to address a related question, on this graph, f of 1, you could either say does not exist or is undefined. I think I used undefined above, so let's go with the DNE for does not exist. That's only because there is an open circle here with no solid dot anywhere, so you can't even calculate f at 1 at all. Makes sense algebraically because you cannot put a 1 in that denominator, you'd be dividing by 0, and even 0 over 0 is undefined. But this is all in orange because these are just related comments. What we really want to do is take the limit as x tends towards 1. So let's take a look at part A. We want the limit as x tends towards the value of 1 of f of x. Well, there's, again, 2 ways to view it. If you're heading towards 1, either you're coming in from the left-hand side, going that way, or you're coming in from the right-hand side. So both directions are important here. If we came in from the left, pretty close to 1, we would take a value here that's below 2. But if I got closer to 1, even still, maybe 0.99 or 0.999, this value would have gotten higher and higher. Likewise, if we're coming in from above, let's say we're about here, we would hit the curve, and now we're substantially above 2. but I wasn't too close. And as you imagine, if I got closer and closer, we would get closer and closer to that value 2 as well. That tells us on this problem, let me fix these. I don't know what I clicked on there. The limit has to be a 2, despite the fact the function at 1 doesn't even exist. Again, that's what's really weird about these kinds of things. It doesn't actually matter what happens at 1. All that matters is what happens nearby. And nearby, the closer you get to 1, the closer this will get to a 2. Any questions, folks, with that first part A? Okay, so I like functions like part A, just an ordinary function. But every now and then you have to look at a function like this, the g of x function. Because of the brackets right here, we refer to this as a piecewise function. In other words, g of x is this function on the piece where x is not 1. And when x is 1, it takes the value 1. That's where that solid dot comes into play. Oh, and I missed a few chats. So Dana says, question for after class, like if we take the fiction example or something else real world, how would we get the random 1, 1 separate from the displayed line? I'm not too sure what you mean by the 1, 1 on that. Let me take a look here. Sorry, Dana, which question were you referring to on that one? The one that had the limit of 2. Okay, gotcha. And another question was, when you tested the right side of 1 and it approached 3, why is the limit still 2? Oh, gotcha. So when we approach the right side of 1, it's not about one single value. It's what happens as you get closer and closer to 1. So a description could look about like this, or an illustration. If we're right out here, yeah, it looks like we have a higher value, maybe 2.53-ish. But what's all about this one, Madison, is what happens when the x-coordinate gets even closer? Let me see how much I can zoom in on this thing and have it still work. I think that's a pretty maximum zoom for us. We got right here, now very close to 1. We would hit about here, and the output looks like it'd be something like maybe a 2.1. And we can make this arrow get even lower, make it become the value down here of a limit 2, just by taking the value we started with, the value of x, get even closer to 1 than that. So the closer you get to 1, if the numbers are settling down to some certain height, in this problem it's a 2, that's why we're getting a value of 2 there in the limit. Yes, Eli, for these particular problems in section 2.3, in an exam or in the homework or on a quiz, I will provide the graphs, and then we just take a look at what the limit should be based on the graphs. And it's when we get into section 2.2, we'll see how do we do this if there is no graph whatsoever in front of us. Doug asks, piecewise is like what if a calculator right? Sorry, Doug, I'm not too sure what your question was about that one. What were you meaning about the piecewise?
Like a what if calculator, like different
Oh,
scenarios.
Yeah, that's absolutely right. So the what if here is what if x is 1, your height is 1, and what if x is not 1, you do the rest of the graph. Yeah, that's a great way to think about it. Almost getting through the chat. Dennis says, oh, that was another chat we were looking at. And Madison says, okay, I think we're caught up on chats or questions so far. Other questions or comments at the moment, folks? Let me know if I missed your question. I'll definitely come back to it. Okay, well, we've got a new function g of x here. Let me take off these lines here so it's not too busy if you come back to the notes. And although it's piecewise, we're still taking the same limit as x tends towards 1. So we'll write this one out as limit, or lim for limit, as x tends towards 1 for the g of x function. And I personally think this one's pretty tricky based on the graph you see above. Anyone see what this limit ought to be? Exactly, Jamie, it's still a 2. And that's kind of the idea we're looking at on the example 1. Whatever the function definition is right at 1 turns out to be totally irrelevant. So if you went back to this kind of trick and just decide to wipe out the graph right at 1, this is the graph you'd be looking at. Let me make that even more gone. Really, in spirit, is no different than the graph on the left. As you get closer and closer to 1 on either side, you're getting closer and closer to the height of 2 on this thing. So the limit on this one is 2. Despite the fact, well, on the left, f of 1 was undefined. There's no solid dot here. But on the right, g at 1 would be equal to 1 because of that right there. So now, here the limit was 2, and the function did not even exist at 1. F of 1 is undefined. Here the limit is 2, and the function is defined. And what about this one? This is an ordinary linear equation. The solid dot didn't even have to be there. It's just to compare what happened on the other 2 graphs towards the left. But likewise, you could take the limit of this one as x tends towards 1 of h of x. As you get closer and closer to 1, the height of the curve gets closer and closer to 2, so it has the same limit. Here as well, h of 1, I shouldn't have said as well, on this one, if you put in 1, you get a value of 2, and it makes sense. You'd be plugging in algebraic here to get a 1 plus 1 for the 2. So 1, 1 at g of x. Yeah, you could think of that as a data outlier for this one particular problem. It's still part of the graph of the function, but this would be considered, because it's not within the line, as you said, this is considered a discontinuity. We'll be looking at other kinds of discontinuities, but this is our first view of it. This one also is referred to as a discontinuity, simply because there's a hole in the graph. And on this curve right here, there is no hole. There's emphasized there's no hole with a solid dot, but they could have taken out the solid dot. But this one is continuous. Due to there being no holes or breaks on the graph of this one. But whether it was continuous or not, all of the limits came out identical. Other questions or comments, folks, on example 2? Okay, I don't want to go too far into the notes with just a couple minutes and some time to spare. So we'll come back to these single-side limits when we come back on Wednesday's class. This will be our stopping point for today. Well, thanks for all the participation, folks. I appreciate these questions. These are very well thought out and definitely the questions you would want to ask when you're seeing this kind of stuff for the first time. So I appreciate it. I'll see you all later on Wednesday's class. We'll be right on example 3 when we come back. Have a great evening, folks, or afternoon.
See ya.
Take care. I have to turn off the share if you're curious, just to